Quantum numbers were developed essentially to give electrons addresses, and they were developed using Schrödinger's equation. And quantum numbers define the various levels of electron behavior and position within the atom. There are 4 quantum numbers that we're going to be looking at. The first one is a principal quantum number. It is an integer, and it is an integer greater than or equal to 1. The principal quantum number describes the size of the energy level. Because it describes the size of the energy level, it also then describes the amount of energy the electron contains. As n gets larger, the size of the energy level gets larger and the amount of energy increases. The second quantum number is the azimuthal quantum number. It is an integer. N minus 1 is its largest value. It can start at 0. Describes the shape of the orbital. When L equals 0, smallest value for the azimuthal quantum number, we have an s orbital. Simplest shape is a sphere. When we move up to L equals 1, we have a p orbital. P orbital is a dumbbell or a figure 8. We are essentially doubling our sphere or putting a waistband on our sphere. The complexity of the orbital shape increases. Our next azimuthal quantum number, L equals 2. L equals 2 is a d orbital. D orbitals, for the most part, are 4-lobed structures. So as we're increasing our azimuthal quantum number, we are increasing the complexity of our orbital. And each L value we go up, we essentially double the number of lobes of our orbitals. So we start with 1 lobe, we go to 2 lobes, then we go to 4 lobes. For L equals 3, now we have the f orbital. Again, we've doubled the number of lobes, so f orbitals, for the most part, are 8-lobed structures. The equations you see by each of these essentially is a Schrödinger equation that gives you the mathematical way to create these orbital shapes. We're not going to worry so much about it. Knowing what the shape looks like for each of the orbitals is probably a good thing, though. The third quantum number is the magnetic quantum number, and the magnetic quantum number is represented by m sub L. It is an integer, and it goes from whatever your value for L is negatively through 0 to L positively. So a variety of choices with L. What the magnetic quantum number does is it tells us the orientation of the orbital. So if we go back and we look at the f or the d orbitals, we'll see that, for instance, in the top left case for the s one, all of the orbitals are on the xy axis. If we look at the second one, they're all on the yz axis. So that's the orientation of the orbitals. That's what the magnetic quantum number gives us. If we look at L equals 3, 3 is the value for L, so that means that the values for the magnetic quantum number would be from -3 through 0 to +3. If we count those out, those are 7 different orientations that we can have. If we take a look at the L orbitals, azimuthal orbitals, we'll see that there's 7 different orientations that we can have. There's 7 f orbitals. So that value comes from our magnetic quantum number. Our fourth quantum number is the spin quantum number. And the spin quantum number describes the spin of the electron within the orbital. The electron can either spin clockwise or counterclockwise, and the spin quantum number is represented by either +1/2 or -1/2. Continuing to look at the behavior of electrons within the orbitals within the atom, we have the Pauli exclusion principle. What the Pauli exclusion principle tells us, first of all, is no 2 electrons in an atom can have the same 4 quantum numbers. And remember, quantum numbers are like the address of the electron, and each electron has to have a different address. The other thing Pauli exclusion principle tells us is that each orbital can only hold 2 electrons. It can have 1, but the maximum number it can have is 2, and when there are 2 in an orbital, they have to have opposite spins. Another principle looking at the behavior of electrons and their locations in the orbitals of the atom is the Aufbau principle. And the Aufbau principle tells us as electrons are being put into energy levels, we put them into the lowest energy levels first and fill those before we go to higher energy levels. Hund's rule is the next description of electron behavior and location we're going to look at. What Hund's rule tells us is that when we have multiple orbitals in an energy level, they're called degenerate, meaning that they have the same energy level. And with multiple degenerate orbitals, I'm going to put 1 electron in each orbital before I pair them up. So here's an energy level diagram. If we follow Aufbau principle, Hund's rule, Pauli exclusion principle, we're going to take a look at how we fill them. So as the orbitals are filled with electrons, lower in energy. So I'm going to put an electron in here, and then I'm going to put another electron in here to fill it before I go to the next energy level. As I go to the next energy level, I'm going to put electrons in it, and I can fill it before I go to the next energy level. Orbitals are filled starting with the lowest energy level, and when I remove electrons, I'm going to start at the highest energy level. So let's go on and fill some electrons in these orbitals. P orbital, I have 3 degenerate ones, so I'm going to put an electron in each orbital. The upward arrow tells me the electrons are spinning in one direction. The downward arrow tells me the electrons are spinning in the opposite direction. So first I'm going to put electrons pointing one way. When electrons are solo in their orbitals, turns out it's lower energy if they all spin the same way. I'm going to go back and pair them up. Moving up to the 3s, and then 3p, 4s. Now the next energy level is 3d. Remember way back when we saw that as the energy levels get further from the nucleus, they get closer together. And it turns out that an empty 3d orbital has more energy than a 4s orbital. Once we put electrons in there, the energy level lowers. So, as we just saw, 4s is filled before 3d. It's lower in energy when it's empty. And it turns out that the 3d orbital drops below the 4s orbital in energy as it gains electrons, essentially like it's being weighted down as if it were a balloon or something. So when electrons are removed, they're always removed, as we said, from the highest energy level. The 3d orbital, as it fills, so we'll fill it up here, will drop below the 4s in energy as it's filled. And so the 4s becomes the highest energy level, so electrons are going to be lost from the highest energy level, in this case the 4s first. Okay, if we take a look at the third energy level, what we're going to see is the complexity of the orbital increases. So as we go from an s orbital to a p orbital to a d orbital, the size of the orbital actually decreases. So in our diagram here, the top row, we've got the s orbital. So we've got the probability diagram for it, and that vertical line tells us the average radius of the s orbital. If we look at the p orbital, it's more complex, and that average radius for the electrons in the p orbital is to the left of where it was for the s orbital. So that means that the p orbitals, the electrons, actually exist in a smaller radius. If we take a look at the d orbital, more complex yet than the p orbital, again, that 90% probability, that average radius for the electrons in the d orbital is to the left even more. Also, if we look at it, the third energy level, 3s, it's the third time we see this s orbital. So we have 3 bumps in our probability graph. 3p orbital, it's the second time we see a p orbital. We saw it the first time in the second energy level. So our graph has 2 probability bumps, because sometimes those 3p electrons can trade places with electrons in 2p. So I can find a 3p electron sometimes in a 2p orbital. That's why that bump is there. Third energy level is the first time I see a d electron, so the probability curve for the 3d electrons only has 1 bump. It's the first time I see it.